So in today's video, we are going to discuss about the Klein-Gordon equation, which is the relativistic part of the Schrodinger wave equation. So let's see how we are going to derive this. But the fact is that there is one more equation which is developed by Dirac, but we are going to discuss it in the next part. This part is going to be on the Klein-Gordon equation and how to derive it. So first of all, to know the derivation, you should have take a course, you can say that, or a book on the special relativity, because it's important to know the special relativity, not only about the basics but also to know about the Minkowski metric, the four vectors and all that stuff, because the Klein-Gordon equation is generally the combination of the quantum mechanics and the special relativity. So that's why you should pick up a book and start studying the special relativity if you haven't studied about this in a great detail. So let's see. So first of all, to know about the Klein-Gordon equation or to derive the Klein-Gordon equation, you have to know some of the stuffs from the special relativity that I am writing here. So first is about the four vector, which is the main four vector that we are going to do is here the momentum four vector. So it's represented in this form, and this is the, you can say, as the magnitude equivalent in our 3D vector. So this is the magnitude of the momentum 4 vector. But what is momentum 4 vector? So you can say that the momentum 4 vector is like the generalization of the 3D momentum in our 4D spaces, you can say that. So that's why here I have taken the dot product of the momentum 4 vector, which gives us the magnitude. And the fact is that in a special relativity you will see that this momentum 4 vector magnitude is invariant. It means it doesn't changes from one frame of reference to other frame of reference. And what's its value? So let's see what is the value of this. So this value is mc whole square, and this is the magnitude of the momentum 4 vector. So you have to know about this, and after knowing this you can generally start the derivation. How? So first of all, how we are going to derive our sign convention, because if you have studied a special relativity, you know there is a sign convention for the components of our 4 vector. Like one sign convention, if I tell you, is this: plus, minus, minus and minus. One sign convention is here, you can minus, then plus, and then plus. You can choose any of this particular thing, it will work well. But in my scenario I am choosing this particular sign convention, and let's see what will happen. So first of all, we are going to write out the momentum 4 vector p mu. So these are the contravariant and covariant form of the thing, you can see that in the notation, and this is equal to the p, and this you can say that subscript 0 means the temporal component or the time component, plus p1 square plus p2 square plus p3 square, which is generally the px, py and pz, and there is extra here, you can see, and this is what called the temporal component or the time component. Sorry, I haven't place here the minus sign because this is our sign convention, and we should write it here. So here it should be 1 minute. Okay, minus, minus and minus. So this is a sign convention. Now what we are going to do is to relate this with the quantum mechanics. How? So if you have studied the quantum mechanics, you probably know that the momentum operator is the minus I h bar, and here is this particular operator. This operator is Nabla operator. You know this is the d square by dx square plus d square. No, 1 minute. This is not the derivative, it's by d by dx plus d by dy and plus d by dz. Okay, so this is a Nabla operator, and this is the thing. Now what we are going to do is that we are going to plug this up. How? So we are going to define this particular operator in 3 dimensions. First of all, px operator. So this is equal to negative I h bar del by del x, and then p operator in the y, which is equal to negative I h bar del by del y, and here pz, and it is equal to the negative of I h bar del by del z. So we define this, and we are going to plug this here in this our momentum 4 vector equation. because px is p1, py is p2, and pz is p3. Okay, so we are going to write this out and let's see what will happen. So here, and also the value that I have written, I'm going to substitute for the magnitude of the momentum 4 vector, which is nothing, is just mc square, and it is equal to the temporal component. So the temporal component of the momentum 4 vector is e by c whole square. How you have to see the derivation in the special relativity. I'm not going to derive it here, but I will give you the hint that first of all you have to write down the derivative of the velocity of the particle with the proper time, and then you can choose the equations and it will finally lead this particular equation. So e by c whole square well, let me write down that what I have. So you can derive this p mu is equals to m, 1 minute in the font. Okay, p mu is equals to m u mu. Okay, so these are the things. What you can do is that you can derive this particular, you can take this particular velocity in the form of the position form as dxu divided by dt, and similarly you can do this for the first x, then y, and then z, and then finally for the temporal component. And after this you will see that how this equation leads. So I'm not going to derive it here, I've just give you the hint so you can derive this. Okay, so now let's see what will happen. Then our sign convention negative, and then negative iota h bar del by del x whole square, negative iota h bar del by del y whole square, negative, it should be okay, negative iota h bar del by del z whole square. Okay, now mc square is equal to e by c whole square, and here it should be, when you do the squaring of this particular term, minus will cut out and this iota will open, which is the -1, and if this -1, this minus and minus will cut out, and the equation you are left is the positive h bar del square by del x square plus positive h bar del square upon del y square plus h bar square, sorry here square, del square by del z square. So this is the equation. Now here I have to substitute the E. So also from the quantum mechanics you can see that the energy is equal to the iota h bar del by del t. So this is the energy operator. So I'm going to substitute this in this particular equation. So let's see what will happen. Now again defining it, mc square is equal to, when you will do this, or let me divide it by c here, then c here, and doing the squaring we are left with negative, because iota will open, and h bar square divided by c square del square divided by del t square. Okay, then plus writing this as h bar square divided by del square upon del x square plus h bar square del square divided by del y square plus h bar square del square by del z square. Now what we are going to do is that we are going to take this mc square on this particular right hand side, and we are left it, and then multiply with the minus sign. So if you multiply the minus sign, suppose that we multiply the minus sign here, what will happen? Let's say the minus, it will become plus. Okay, so here it will become minus, here it will become minus, here it will become minus. I'm multiplying it minus. Okay, so if I do this and transfer this on this particular right hand side, let's see what will happen. We are left with h bar square divided by c square del square divided by del t square, and here negative of h bar square divided by del square divided by del x square, and negative of h bar square del square divided by del y square, finally negative of h bar square del square upon del z square, and finally positive of mc whole square, and finally equating this as 0. Now h bar square. I'm dividing the whole equation by h bar square. So this will become 1 by c square del square divided by del t square, and taking negative common, you can generally see that this equation is nothing but the Laplacian, which is del square upon del x square, because here you can see minus del square divided by del y square, and positive del square divided by del z square, plus mc by h bar whole square, and equals to 0. 1 minute. Okay, equal to 0. So as you can see that this is Laplacian, and if I substitute this Laplacian, or you can say that 1 by c square del square divided by del t square negative this operator square, and then positive of mc by h bar whole square is equal to 0. We simplified this particular expression because this is the nabla operator whole square. Okay, so now what we have to do is to simplify this. We have arrived to this equation. This is the Klein-Gordon equation, but we have to summarize this equation a little bit more. So what I will do is that you can see that this particular thing is nothing but this. You will say what I have written here. So the fact is that this is called the D'Albertian operator. D'Albertian operator. So we are going to do this. So it will become then this square like thing, and then multiply this equation by our wave function to operate to give something. So 1 minute here. M square c square h bar square multiplying with wave function, and it is equal to 0. Finally we have arrived, and this particular equation is called the Klein-Gordon equation or Gordon equation. Another substitution I'm going to do, what I'm going to do to simplify this a little bit more, is this D'Albertian plus mu square psi is equal to 0. Now we simplified it a lot, and this is the final expression that we are left. This is the final expression. You will argue that what I have done. So the fact is that I substituted mc divided by h bar as mu. So then this whole square will be mu square, and I substituted this mu square here in this particular equation, and we are left it with this particular wholesome relativistic equation, the Klein-Gordon equation, the Klein-Gordon equation. So the fact is that how the relativity combined beautifully with this particular Schrodinger wave equation to form a new equation called the Klein-Gordon equation. But remember, this equation is only for the spin zero particle. That's why we have to also derive the Dirac equation, which is the topic of the next video. But what we are going to do is that we are going to understand the solution of this particular Gordon equation, Klein-Gordon equation, and what the solution of this equation tells us. We are going to study, just like we have studied wave function, we have studied Schrodinger. Then what we have done is that we have tried to understand the solutions of the wave function, that how it depends and how it behaves in different potentials, all of that stuff. Just like this, we are going to decode this particular equation, and we are going to solve for the different types of things. Let's see what the solution of this particular Gordon equation represent and how it is different from the Schrodinger wave equation. So this was my video, and if you have any difficulty, because here the quantum mechanics is combined with relativity, so you can read a book on the relativity by AP French. AP French is a book on relativity. You can use this particular book, or I am planning also to make a series on the special theory of relativity, like about 4 vectors, all of that particular topic which we will encounter in the quantum field theory and the relativistic quantum mechanics. Okay, like 4 vectors, and like the Maxwell equations, and how the Maxwell equations related with the special relativity, invariant, covariant, and the tensor notations and all of that stuff. So this is a video on the derivation of the the Klein-Gordon equation with the special relativity part. If you have any doubt, you can write down in the comment section. Thank you.